Welcome back to the video series. Today we'll be doing the repeated measures t-test. But in order to really have a better understanding of that, we're going to have to review a bit, revisit some of the statistics that we've already covered, and add a little bit of understanding of probability and what's actually going on when we do an experimental design. So to do a bit of a review, if we look back at the one-person z-test or z-test for an individual, what we had in this case is we had actually one score as indicated by the x value. We would subtract that observation from an existing mean. So that's the actual observed difference. Why do we call it the observed difference? Is because I actually measured that one score and subtracted that difference from a known population mean. So now I have to compare that to the expected difference or the standard deviation. Remember, the mantra for that is conceptually the average distance of an observation from the mean, what we would expect an observation to be away from the mean. And so really what this is happening here is this is expected or estimated by probability and statistics. So we have the observed difference over the expected or estimated difference. If the observed difference is large enough, then our z-statistic will get larger. If our z-statistic gets above the critical values of plus and minus 1.96, then that indicates that it is significantly different from what we would expect by chance. Similarly, if we are doing a z-test for a group, well, at this point, we are not dealing with an individual observation, one observation, but we're actually dealing with an average that we compute from multiple observations. We are still looking at the difference of that average from the population average. So we're looking at a difference from a mean from a population mean or a mean from the mean of the means, because remember here, when in terms of what we're dealing with, those are effectively the same thing. So we can no longer rely on the statistics of a sample, which is the distribution of individual observations, but we now had to move to a sampling distribution, which is a distribution of means. So the denominator for the z-group formula is standard error, which, remember, the mantra for that is conceptually the average distance of a mean from the mean of the mean. So how far away on average do I expect any a group average to be from the mean of the means or the population mean. As we moved forward to the t-test for a group, that was effectively, again, exactly the same thing, but with that t-group formula, we did not know the population standard error or population standard deviation to get to the population standard error. So therefore, we had to estimate it with the sample that we had. So we had x bar from the sample, and then we estimated what that sampling distribution, the population sampling distribution, would look like based on the actual sample that we had. So instead of sigma sub x bar, we have S, capital S sub x bar, indicates that it's an estimate, but because it's an estimate, we lose a little bit of confidence, so we also lose a degree of freedom, and our critical value ends up going up from plus n minus 1.96, because that would be an infinitely large sample, to a larger and larger value based on the size of the sample that we have. So what is actually happening when we're doing an experiment and we're testing a treatment of some sort? Well, with a Z group and a T group, really what we have is we have some population. We have some overall set of complete observations, and we're taking from that a sample. Then we take that sample and we're going to have some treatment that we're putting to that sample. So our null hypothesis is basically the world in which the treatment has no effect. So imagine if we have a sample, we administer some treatment, but if the treatment has absolutely no effect, zero effect, then our sample has not changed at all. It is still a sample from the original population, and if it has no effect, it will return literally to exactly the same place in the population from which it is drawn. So both practically speaking and statistically speaking, we accept the null hypothesis. We applied a treatment, the treatment did nothing, therefore we accept the null hypothesis, and the sample returns to the population as it was. However, if the treatment works, this is a different world. What happens is we have the sample, we administer the treatment, but if the treatment now works sufficiently, then what's going to happen is it now will fall statistically into this critical region. If the treatment works, the sample is no longer considered part of that original population from which it was pulled, because it is no longer just the sample, it is now the sample plus the treatment. Let me put this in relatively simple terms. If I have a brunette and that brunette dyes their hair and it works, then when they go out in the world, they are no longer a brunette. They are now a blonde, if it will be. So the sample plus the treatment means you are no longer a brunette. You have now become part of a new population, a new group, which is sample plus treatment. In this kind of absurd example, you are now a blonde. So literally, that group of individuals, when the treatment works, is no longer part of the original population. It has now become something new. That is the population of people with treatment, is ultimately what it comes down to. So with both Z group and T group, you just have one sample and you're seeing what happens to that sample. So here we have kind of a perfect world. We have when the null hypothesis is true, the treatment does nothing, nothing moves in terms of the sample, and so it remains where it was. We have the reject the null hypothesis in favor of the experimental hypothesis. This is a case where the sample, the treatment is applied and it works, and it drastically changes those individuals. So now that is the group plus the treatment. It is now part of a new distribution, a new population. But there are variances on this. There are different things that can happen. So again, we can have a situation where remember we have this population from which we are drawing a sample. On the previous slide, that sample came from the middle of the distribution because that's normally what happens. Anytime that we draw a sample, we expect it to come from the average, the middle of the distribution. However, it is possible, just through random chance, that when I pull my sample from the population, I actually happen to get an extreme group of individuals. So to revisit what we were talking about from a previous video, even though it's highly unlikely that I walk into a store with 500 individuals in there and I randomly point at 10, that they would have an average height, those 10 individuals would have an average height of say 6'7" or 6'5" or even 6'3", even though that's highly unlikely, it is possible. There is the chance that that could happen. So now imagine a situation where my original sample, the sample that I pull, starts off in the extreme range. I then apply the treatment to it. Even if the treatment has no effect whatsoever, when I compute the statistics because of where that group started, it will look as if the treatment worked. This is what we call a type 1 error, because this is basically the worst case scenario. The treatment has done nothing, but the statistics tell us that it does. We definitely don't want this to happen, because imagine a situation where you're testing, say, a cancer treatment. If the statistics tell us that the cancer treatment is working, but it's got very bad side effects, but in the real world it is doing nothing, what that means is it is not helping you at all with the cancer, but it is, in addition to the cancer, giving you the side effects that come with that medication. So this is why we consider this a type 1 error. This is not a situation that we want to have happen, but it can happen. Typically speaking, or conceptually speaking, the chance of that is essentially equal to alpha. There's some quibbling that we could make over that, but basically there's a 5% chance that this can be the situation. What is another situation that could occur? Another situation, again, is that when we randomly pick a sample from the original population, remember that sample could come from anywhere. It could come from the extreme range, as indicated here. It could come from the center of the distribution, but slightly to the negative side. It could even come from the significantly negative side, but for now we'll stick with this. Let's say we have a sample. These are regular individuals. We then apply the treatment. The treatment does work, but in this case, the treatment moved it towards the positive side of the number line. And as we look at it here, because we started off with a sample that was already to the left of negative, even though that treatment worked, statistically, it is not past the threshold for significance. So here is a situation where we have a type 2 error. The treatment in the real world did work, but the statistics when we compute it indicate that it did not work. So the reach of that natural variation was such that the treatment did not extend past what we would effectively consider noise. It doesn't move the sample enough. So even though really in the real world this is now sample plus treatment, statistically it still belongs in the original group. So is there anything that we can do in this situation? Because again, ideally, you need a sample plus a treatment that is sufficient to overcome the natural range or variance of the observations that we find in nature in general. Because remember, those observations can be very widely spread to very narrowly spread depending upon what you are measuring. There are ways to basically deal with this, because really what we're looking for when we say we want that treatment, we want to measure the treatment statistically, that's the signal that we're trying to find in statistics. The range or the variance of this distribution which we're talking about is the noise. We need to be able to hear the signal above the noise, which is random variance within a population. So if I have a weight loss drug, that means that your weight is going to change to the negative, but people's weight fluctuates in general. So what happens is that change in your weight because of the drug needs to be large enough that it is distinctly different than that random fluctuation that we see in weight change across people in general. So either I need a stronger drug. So in this case, if I cannot change the population in general, that variance of weight change in people in general is going to be there. I can't do anything about that. Then I need a stronger drug, or maybe there is a way that I can change the distribution, the shape of the distribution itself. If there's a way that instead of having this very wide variance that we see in the original distributions, maybe I can narrow that distribution. If I can narrow that distribution, then even though when I look at these, the distance from this one to this one is the same as the distance from this one to this one, meaning the effect of the treatment is identical in these two pictures, but on the picture over there, it is now in the critical region. The reason why is because I have shrunk the variance of that distribution, and by so doing, that amplifies, it doesn't amplify the treatment, what it does is it reduces the noise. By reducing the noise, I now statistically am able to see the treatment. So how can we accomplish that? Well, again, remember, we have natural variation or noise, and there's two forms of natural variation. So if I have a sample, so in this case I have my original population from which I am drawing the sample. Anytime I draw a sample, it could be any one of these just by chance. So if I'm dealing with, say, two groups, which eventually I will do, then what will happen is I could draw this sample here, and the other sample might be this one here. So you notice, because these are samples of different people, there's going to be natural variation between those two samples. So simply because I am using different groups, I expect there to be measurement difference between those samples, because the samples are comprised of different individuals. Similarly, within any one of these samples, so if I just take one of these samples and I plot the measurements out into a distribution, because that one sample is made up of different individuals within the sample, I also expect the measures within that sample to be different, because it's different individuals, or in this case, back to the fly example, it's different flies. I don't expect all of the flies to have exactly the same length of wings. They are going to have differences within the flies in that one group. So I have what we call between groups variance, because this group is different than this group is different than this potential group. That's differences between those groups, but then because I have different observations within a group, I know that there's also going to be differences within that group. So there's two types of variance, between groups and within groups. So any of those samples could be randomly selected as the control group or the experimental group, so I know that I'm going to have almost certainly some variance between those groups on top of the within groups variance. But what if I have one sample? So what do I mean by this? I take a sample, I take the measurements, and then I apply the treatment to all of those individuals. So I have the measurement before the treatment, I now apply the treatment, and now I have the measurement after the treatment. Think about this for a second. If the treatment has zero effect, no effect whatsoever, then should the measures before be expected to be different than the measures after? And remember, we are also at this point talking about the theoretical perfect world. In a theoretical perfect world, if it's the same individuals, so I have a sample that's going to be made up of different individuals, I will expect the within groups variance, but if the treatment has no effect, then the before measurement should be exactly the same as the after measurement. So by using the same participants, the natural variation, the noise, should be reduced because we will be getting rid of the between groups variance. So I'm going to revisit this on the next slide just so that we can really truly understand this. The amount of natural between groups variance should theoretically be zero, but if nothing else, should definitely be reduced. So if I have, here I'm just dealing with two participants, so I have a sample of two participants. They're being measured on something, perhaps in this case it's minutes to complete a task. Participant 1 maybe took 45 minutes. I don't expect participant 2 to take 45 minutes because they're a different person. So within this sample of two individuals, I still have within groups variance. However, if I then apply a treatment and the treatment does nothing, then if it took participant 1 45 minutes, then on the next time that they attempt this task, it should also take them 45 minutes if we assume that practice effects have no effect here. Likewise, participant 2, if it took them 63 minutes on the first time, then as we get to their second trial, it should also take 63 minutes if the treatment had no effect. So again, if we have before minus after, again, theoretically, that should be zero. So if I were to calculate a mean for that expected difference for before and after, if the treatment has no effect, it would be zero. So again, to reiterate with a slightly larger group, here you notice that we have zeros across the board because in the theoretical perfect world, those different scores and the average of those different scores, so here I would have 0 divided by n. In this case, I actually am showing you 5 participants, but I'm just indicating n because I could have as many as I would care to. 0 divided by any number is always going to be equal to 0. So that's the theoretical world, but in reality, we know that the measurement before and after aren't going to be completely in sync. However, they're still going to be much, much closer. So if we look here, even if the treatment has no effect, that after score, even if it's not exactly identical, will still be much, much closer. So the theoretical mean is 0, and now we go back to the previous video, because remember, populations. There were special occurrences when I could call something a population. One occurrence was when I had measured absolutely every possible observation. I'd actually measured it. So for our example in an earlier video, we were only concerned with the houseflies in our person's house, and we measured all of them, and we weren't comparing to any other flies. Therefore, because we had every single measurement, that could be considered a population. But as we move forward, the other special case was in situations where probability told us what the average should be. So if I had a 6-sided dice, then I know if I rolled that an infinite number of times, or even approaching infinity, because I don't have to get every possible measurement, we know that the average for any one number on that dice to show up is going to be 1.66 repeating, or 1.67 if we average it out. So now in this case, why this works is because probability tells us that over an infinitely large number of samples, even if some of these are slightly higher than 0 and some of them are slightly less than 0, in the end, when I add them up, I'm going to have 0. So what does this tell us? We know now that we have a population mean of mu equals 0. We have a population parameter. So once we have that, even though in the real world we know it's going to vary a little bit from that, we can still use a statistic that allows for a population parameter. So in this case, even though we're going to have some variance, we know it's going to be much less, we know what that theoretical amount is going to be, the repeated measures t-test is exactly identical to the one group t-test that we did in the previous video. That's why I added that video that some textbooks do not have the one group t-test, because I want you to see the progression. The one group z-test looks just like the one group t-test. The one group t-test is identical to the repeated measures t-test. The only difference, instead of using the x variable, we're going to end up using a d variable, and we have to take one additional step to get there. So let's look at how that plays out. Let's remind ourselves very quickly, this was the one group t-test that we did from the previous video. So what does this mean? We had our actual distribution of numbers right here. These were the actual measured values. We calculated an average of 85 on those values. To get the sum of squares, what did we do? We took each individual value, we subtracted the mean from it, we got that total, we squared it. Once we did that for all of them, we summed them, hence the sum of the squared deviations, or sum of squares. Once we had the sum of squares, we were able to get the standard deviation, which allowed us to calculate the standard error. So now we know the expected difference of a mean from the mean of the means, the denominator. Once we had that, we were able to actually calculate our t-value for one group, because in our previous example, probability told us that if the birds remembered nothing, they should dig up 50-50 in terms of worms versus nuts. So again, here's our statistic as we knew it before for the one group t-test. I want you now to look at, this is the repeated measures t-test over here. The repeated measures t-test on the other side is identical to the one group t-test. The only difference is here I have x bar, over there I have d bar. Here I have standard error indicated as s sub x bar. Over there I still have standard error, it's just s sub d bar. Because instead of dealing with what we had labeled as an x distribution, we're now going to be dealing with what we will label as a d distribution. If you can compute one group t-test, you've got repeated measures t-test. So how do we do this? We have to add one step. So I have all my participants here, participant 1, participant 2, participant 3, participant 4. That's just a shorthand for indicating that. The story problem that we're having here is a question of, if there's a difference in the accuracy of marksmen, if they pull the trigger when their heart is beating versus between heartbeats, is that slight tremor of the heartbeat enough to slightly nudge, to create a small movement where it's going to make the gun basically not be where you want, and the shot goes off a little bit? This is not a pure before and after design, but it is still the same group doing the measurement in one condition, and the same group, the same people exactly, doing the measurement in another condition. So we don't have that between groups variance. It's not one group during the heartbeat and another group between the heartbeats. It's the same people, so we've now wiped out that between groups measurement. So we've lost that variance, so our noise is going to be less. So what is your first step? You have to subtract 93 minus 97 to get your different score. So this very first row of numbers will be doing the subtraction between those two. It does not matter which direction that you do the subtraction. I could subtract 97 from 93, or I could subtract 93 from 97. It doesn't matter which way you do it, as long as you are consistent the entire time. So if I do 93 minus 97 equals -4, and the negatives are very important here, then 93 minus 97 equals -4, then the next one must be 90 minus 96 equals -6. I can't switch up which way I do them because those negative signs are very, very important. So once I create this first column here, that will just be the subtraction. Now, once I have that first column, I can calculate the mean of those scores. Again, be careful with the positives and negatives because you need to get those carefully when you're adding them up. So once I have that column of different scores, that's what that first column is going to be, this will work just like the t-test that we did before. Instead of my column of X scores, I will have D scores. I will calculate a mean. For this original t-test that we did, that mean was 85. I'm going to subtract that mean, get the difference, square it, and then get that squared value so I can sum it together. So what are the blanks that I provided you here? That very first column here is going to be your difference scores. Then this next column, you'll want to fill that in with all of your means, just as we have in the yellow over there for the t-statistic, for one group t-statistic. So it's going to be the difference minus the mean of the differences. Then once I have that value, I'm going to square it, and then I'm going to take those squared values and add them up, and I will have the sum of squares. So subtract, get the differences. Add those differences together to get sigma d. In sub d now you have to be careful about what is in. I have 9 participants, so is it 9? Is it 9 plus 9 is 18? Is it 9 plus 9 plus the 9 for the different scores is 27? What it is the number of, in sub d, the number of different scores. So I'm going to have 9 pairs of numbers, so after I subtract, I'm going to have 9 different scores. So I will get sigma d, I will get my 9 scores, then I'm going to want to calculate d bar. What's the average of those 9 scores? Mu sub d for a repeated measures t-test is always 0. So you can immediately and every time when you create your toolbox, fill that in with mu sub d equals 0. Once I have my d bar, as I told you, you can then calculate your sum of squares. Once you have sum of squares, you can get your standard deviation and your standard error. I have provided those, sorry. I have my formula for standard deviation up here. Sorry, this is standard deviation here. It's going to be the sum of squares for those different scores divided by n sub d minus 1. Remember, we're using this as an estimate, so we're going to lose that 1 degree of freedom. Once I have the standard deviation, I can then calculate my standard error term. Once I have standard error, I'm able to do my t-statistic. So at this point, what I encourage you to do, and use the yellow as a reference to help you through, pause the video, go through and compute all of these values until you get your final t value. Remember, that's going to be t for degrees of freedom 8. I've provided a partial t table here so that you can look up the critical value for that. Make your decision, should I reject or accept the null hypothesis, and then try to interpret your statistic. Welcome back. If you've successfully computed, then your values should look like this. So as we said before, I take 93 minus 97, that gives me -4. After I compute all of those, I'm going to get a -27 for my value. Then, once I have 27, -27 divided by 9, because I want the total number of observations here, I don't lose a degree of freedom, that's going to give me a mean of -3. -4 minus a -3 ends up being -4 plus 3, which gives me 1. I square that, I get 1. I do the same for the rest of the values. I end up getting a sum of squares of 111. When you plug the rest of those into the values, you should end up getting 3.72 and 1.24, finally leading to a t of either -2.42 or positive 2.42. It doesn't matter which way you subtracted. All this will tell you, all that value is going to tell you is whether or not to accept or reject the null hypothesis. The critical value for a two-tailed t-test in this case is, as you see down here, plus and minus 2.306, as negative 2.42 is outside of that critical region, we are going to reject the null hypothesis. So now, what do we want to do? We want to look at these values, and in fact, I didn't do it here, but it very much helps to go ahead and calculate the average of the during score and the average at the between score. But in the end, if you just look at the values, the between numbers are higher than the during numbers. Don't worry if this value here is positive or negative, because you have to interpret relative to the original numbers. So the between values are higher. Higher in this case indicates greater accuracy. So what does this mean? Our null hypothesis would be that there was no difference between accuracy if you were firing during the heartbeat and between the heartbeat. But because we have a significant t-value, this indicates there is a difference. And when we go back to the original values, we have higher values in the between, meaning that the marksmen were more accurate when they pulled the trigger between heartbeats than during heartbeats. So that is how we end up interpreting it. Because this is negative, sometimes on occasion, when I have students doing this, they see negative, and so they immediately think, oh, they got worse. Remember, all this tells you is yes or no, reject or fail to reject. The interpretation must come from the original values. So once you've made that decision, ignore this number, look at your original values to help you decide that. So that has been the repeated measures t-test, t-statistic. As I say, this is going to help us make progress towards what we're doing. Your book should have some practice problems on this. If not, just again, go to Google, do a repeated measures t-test, practice problem, or sample examples. That will give you a chance to spend some practice time on this, and it's going to reinforce everything that you've done to this point, including the one group t-test and the one group z-test. The next video will be independent measures t-test, which is really just an extension of what we've done to this point.